Hello and welcome back to the channel Understanding Concepts of Physics. Subscribe the channel in case you haven't done so. And today we have been doing since past few videos the topic of processes, different types of thermodynamic process we have been doing. And today we are on to the last and the second last types of process. One is called as the cyclic process, as you can see on the screen, and the second process is what is called as the free expansion. So there are these two processes which we are going to do today, and the first is the cyclic process, the process which repeats itself between its initial and final state is called as a cyclic process. So you can see the cyclic process can be of any type. It could be isothermal, it could be adiabatic, it could be isobaric, isochoric as well. But if the process is getting completed and again it is happening, then such kind of process is called as a cyclic process. So a cyclic process is just toggling between its initial and final state. This kind of process is called as a cyclic process. So let's say if we see, we can have a PV diagram for that. So let's say we have a pressure axis and a volume axis, and there is this initial state A whose initial volume is Vi and the initial pressure is Pi, and there is this final state B whose final volume is Vf and final pressure is Pf. Let's assume that the process goes from A to B in this pattern from the curve which is in the lower side, and then it goes back to the initial state from the upper side, and it keeps on doing that. A to B, then B to A, and then A to B and B to A, and this process keeps on continuing. Then such kind of processes which repeats itself in between initial and final position is what is called a cyclic process. Now you may wonder, how is the work done calculated? Now if you remember, when we were doing PV graphs and other kinds of processes, we have discussed that the area under the graph gives you work done. This is what is the work done. So what would it be in a cyclic process? So in a cyclic process, the area inside the graph gives you work done. So whatever is colored here will show you the amount of work done. Now you will say, okay, how is this possible? So what we can do is we can bifurcate this graph into two parts. Let's say I have this one graph, one y-axis, x-axis, and the graph looks something like this. And now if I wish to find out the area under this graph, then this would be that area, and this would be that area. Okay, so if I wish to find out the area, then the area would be this part. This would be that area. Now because this is the initial volume and this is the final volume, we'll say that the volume has increased while going process from initial to final. So A is your initial state and B is your final state. Now because the cyclic process is again going back to its original values, so let's say this is that, oh my god, it is going to its initial state somewhat like this. Then now it is going from its final state to its initial state, final volume to its initial volume. That means the volume is decreasing. Now in this case the area would be somewhat this one. I would paint that in red. This one, this red area would be the area under the graph. So while going from initial state to final state and while going from final state to initial state, the amount of work done, that is the amount of the area below the graph, is different. For going from initial to final, this graph, the area was only this much, but while it was going from final state to its initial state, the area is so much. So if we subtract the area between these two, initial and final, you will find out that the work done is basically the area inside the graph. Also, there is one more point we can add over here is, now if you see, when you find out the area under this graph, this first graph, this is a smaller area, And when you find out the area under the upper graph, that is the final to initial state, the graph has a greater area. Also note that while going from final state to initial state, it is going from a final volume Vf to its initial volume Vi. Final volume is greater and initial volume is smaller. So if you see, anti-clockwise final minus initial will give us a positive work done while we are going from this point to this point. What does it imply? If the change in volume is positive, dW is nothing but PdV. So if dW is equal to, just a minute, dW is equal to PdV, and if dV is positive, dW would also be positive. But if dV is negative, dW would be also negative. It implies that if I am going from some initial state to final state, final volume minus initial volume will give me change in volume. But if I am going from this point to this point, that means my volume initially was large and finally it was less. So final minus initial will give me a negative number. So going on the reverse side, the work done would be negative. Going on the positive side, the work done would be positive. Because the positive side area is lesser and the negative side area is more, the net work done would be negative. So anti-clockwise motion of the process or the direction of the process will give us negative work done. So this is going to give us negative work done. However, had this process been the other way around, suppose if the process was going from this point to this point and this point to this point, that means it was a clockwise process like this, then the work done would have been positive. But because it is anti-clockwise, the work done is negative. So we can conclude here that anti-clockwise process, I will just write over here, anti-clockwise process, work done is negative, and clockwise process, work done is positive. So this is the way how it works. So this is all about cyclic process, nothing more, nothing less. You can take a screenshot if you wish to. I just halted the screen as of now. Okay, so hope you have taken the screenshot. Now we will move on to something called as free expansion. A very simple process, very easy to remember. Free expansion is a process in which we have fast adiabatic expansion. So adiabatic is basically like your heat is kept constant. The process is fast, that means you should not move, you should be moving the piston very fast, up or down, and it's an expansion process. So basically the piston is moving upward and it is called as a free expansion. So free expansion is nothing but fast adiabatic expansion process is called as free expansion. The best example for that is bursting of a tire or a balloon. So when a tire bursts, the air actually comes out of the tire instantly in a few seconds. However, make sure that we are not talking about puncturing. In puncturing, the air comes out slowly and gradually. So bursting of tire is one of the best examples for free expansion. Now free expansion process does not have a PV diagram. It does not contain that PV diagram because the system is in highly inequilibrium. So system is not in equilibrium. That's the reason why we do not have a PV diagram for a free expansion. So these are the two processes. However, there is one more process called as the quasi-static process. Quasi-static process, which I think so I have not discussed. Quasi-static process. Now this process is basically a process in which things are happening very slowly, extremely slowly. So when process happens very slowly, we call it as a quasi-static process. Normally thermodynamic process is considered to be quasi-static, and the reason is we want that the piston should go very slowly, or very slowly expansion or very slow compression has to be taking place. Otherwise, if the process is happening very quickly, then we categorize that into free expansion, and even the momentum of the piston will also be considered if we are moving the piston pretty fast. So that's all for types of processes and for the today's video. Thank you for watching. If you are still with me, subscribe the channel in case you haven't done so, and keep following the video from the playlist because there is a link of all the videos. Thank you so much. Bye.